I'd like to thank the organizers for inviting me to this special event. And let me first say that, so I'm currently at Max Planck Institute for Astrophysics in Garching, Germany, a suburb of Munich, since 5 years ago. But before then, in my former life, I was a proud Texan. And why do I bring this up? Because, so Cook's Branch is a very fantastic conservancy in northwest of Houston. And you wouldn't expect to see anything like this in Houston. It's a fantastic place. This place is owned by George Mitchell, who supports science and kindly donated lots of money to Texas A&M University, rival of my university, Austin, Texas. But we're all friends talking about physics here. Now, why do I bring this up? Because when George Mitchell was asked to found this George Mitchell Institute for Fundamental Physics and Astrophysics, he asked for one condition, which is to tie the institute to Stephen Hawking. So he will come to this place, I think almost every year. And I had a few opportunities to see him in this place. And this is a perfect place to talk about cosmology, black holes, and gravity. We had sometimes lots of wine, even for lunch, but that was a perfect place. So this is my little personal connection to him. So I'm going to tell you about how to find inflation, or how we found it, how do we find it, how do we make progress. Our main tool is the cosmic microwave background. And so you see here our view of the Milky Way. And what I'm going to show you is how the sky would look in different wavelengths. We first go from optical, and we gradually increase the wavelength so that we go to microwaves, centimeter or millimeter wavelengths. So visible, infrared, far infrared, some millimeter, but by the time you go to microwaves, millimeter, centimeter, then sky is filled with this remnant, remnant of the fireable universe. That's the light that was emitted when the universe was 380,000 years old. But if you then improve your sensitivity of the detector by a factor of 100,000, then you start seeing these ripples. So these are the initial irregularities that existed when the universe was born. Now, what's the big deal? So this is the distribution of photons. Doesn't necessarily tell you the distribution of matter, but using laws of general relativity, you can connect them because gravity shifts the energy of the light, the gravitational redshift. But also, you need to specify the initial conditions, how photons and matter were distributed initially. And by making trial and error kind of study, we discover that so-called adiabatic initial condition, basically when matter is there, photon is there as well in proportion. But since photons have to climb up against the potential well before they escape from this elastomagnetic surface and reach us, they lose energy from the overdense region. Therefore, you have to calculate, right? So how much photon temperature was there at the bottom of the potential well, and how much energy was there once they escaped. And it so happens that this standard adiabatic initial condition that we discovered using WMAP, it's a cold spot that's overdense. And if you zoom into this overdense region, you start forming stars and galaxies and planets and eventually ourselves. So the remarkable story is that we seem to now have a pretty good idea about where we came from. So if your kid would ask you, Mom, where did I come from? You first say, here, right? Right there. But then they will ask, well, where were you from? And then your grandmother and grandgrandmother, grandgrandmother. And eventually you go to, say, Earth. Where did Earth come from? And then you say, so I think I remember learning this in my astronomy class in college. Protoplanetary disk, or sun, or Milky Way. Then they will ask, where did the Milky Way come from? Then you are like, go to bed. It's none of my business. But we seem to now know that partial answer to it, and I think that's just fascinating. So what generated these initial fluctuations? The leading idea is that it's a quantum mechanics. So we all came from quantum fluctuations. That's the leading idea. I think many people are convinced of this. I'm also pretty convinced of it, but we basically want to work more to convince everybody else, right? But quantum fluctuations, that's fine. So universe was, in the early universe, the visible universe was small. And it's so small that you can't ignore quantum mechanics. So quantum mechanically, fluctuations are produced. But you still need to, because in this room, there are quantum fluctuations too. But they never matter on larger scales. So what's the missing link connecting small and large scales? And that's cosmic inflation. So you have these quantum fluctuations in microscopic scales. Inflation, this crazy exponential expansion that will take something of the size of atomic nucleus to the size of the solar system in 10 to the minus 26 seconds or something like that. Truly remarkable, if not crazy, way to explain the origin of our universe, origin of our structures. Crazy, but could be true. And in fact, all the data we have collected so far in cosmic micro background are in excellent agreement with this idea. So no matter, and that's a great thing about this studying universe, because something that seemed very, very crazy turns out to be almost correct. So key predictions of inflation, among other things, is that they generate quantum mechanically scalar modes, which are basically gravitational potentials. These are galaxies. And tensor modes, which are gravitational waves. And we're trying to look for the evidence of, well, we measure the scalar mode very well, and I will tell you what we learned from it. The next goal is to find the tensor modes, these gravitational waves. So they quantum mechanically generate perturbations to the distance between 2 points, so spatial metric. And overall, the universe is also expanding. So you have this A factor here that increases over time. And zeta here is the perturbation to the determinant of spatial metric. So that will change the distances between 2 points isotropically. Hij, gravitational waves, is not perturbing the determinant. So it will perturb the space-time such that the whole area of this distribution particles will be conserved. So let's look at this A, because this will define inflation. Inflation is the accelerated expansion. So you take the second derivative of A, divide that by A itself, and you, by simply using the definition of this capital H, which is A dot over A, you discover that you need to have this epsilon. That's a ratio of H dot and H square times minus, has to be less than 1. And in fact, that's not quite sufficient to explain our universe. Our universe, within the observable universe, spatial geometry of our observable universe seems like flat Euclidean space. So to homogenize, to sort of smooth out curvature to such a sufficiently large scales, it's a well-known fact that the inflation has to have a sustained period, at least 50 eFols. So that will put much severe bound on the value of epsilon here. Namely, epsilon has to be basically of order 1 over n or less. So 10 to the minus 2 or less. So that's what we want to find. Now, to achieve this, of course, you need to measure h. And somehow you need to map out h as a function of time. How do you do that? Astronomers know how to map h of t as a function of t. It's called Hubble diagram. So we're trying to do the same thing for the early universe. The key here is that both scalar and tensor perturbations are proportional to h. And at the with the risk of sort of saying something incorrect, but for the purpose of being pedagogical, let me say, so this is a consequence of the uncertainty principle. In principle, you can borrow energy from vacuum if you promise to return it soon. So the amount of energy you can borrow from the vacuum is inversely proportional to the time you borrow. And that 1 over time is basically the same dimension as the h, because h is a dot over a, right? So this tells you that this energy you can borrow, or zeta and hij, should be proportional to h. Now, here's the most important part. Inflation continuously generates perturbations. Once perturbations are generated with a given wavelength, they're stretched. Then in the next moment, another perturbation is generated and it's stretched, but it's stretched less. Therefore, the earlier the fluctuations are generated, the more they experience the stretching, hence, the larger angles they subtend in the sky. So all we have to do is to map out the amplitude of fluctuations as a function of scales, as a function of angles. So first of all, we want to show that the amplitude of fluctuations in cosmic micro background does not depend very much on angles. Second, because inflation has to end, this function h decreases. In fact, it decreases for deeper reasons as well. And we want to show that, in fact, there will be a slight deviation from the exact equalness of the amplitude of fluctuations. In fact, it should decrease over time. Therefore, it should decrease as you go to smaller angles. That would be fantastic to find it. In fact, we found it. That's what I'm talking about here. So let's do the data analysis. We take these temperature maps and decompose them into a set of cosine and sines, and then plot the amplitude of waves as a function of inverse wavelength, so wave number. And here we go. So that's the so-called power spectrum that we measure using WMAP satellite. And well, x-axis is the inverse of the wavelength, y-axis the amplitude of waves. And as you can see, it oscillates. It doesn't go like equal amplitude or decreasing or increasing monotonically. It's doing all kinds of things. So what's going on here? But before we go there, let me just explain what the power spectrum is once again, because it's an important concept. So if you're looking at the leftmost region in this plot, then you are looking at wavelength that's as big as the whole sky. Then as you go to the right, you start seeing smaller and smaller wavelengths. And by the time you've done your job and you measure all the modes, you combine them back again, then you get the original map of cosmic micro background. Right? So it's just Fourier analysis, nothing else. Very simple. So what's happening here? So let's take a look at this signature soup in Japan called miso soup. And so basically my point is that the universe is a bit like miso soup before the universe became transparent to photons. What's the idea? So you have this soup, plasma, consisting of photons, neutrinos, electrons, helium, hydrogen, and dark matter. And you drop tohus, if you know what they are, or potatoes if you're German, and then they start creating ripples. And depending upon how much miso you have in there, or how much beans, how much whatever in there, you discover that the way the waves excited are different. And also, these soups are actually viscous, not completely perfect fluid. So waves that are excited damp. And the way they damp also depend upon the composition. So if you change, for example, the density of hydrogen and helium, this power spectrum peaks change. If you change the density of total matter, it changes in a different way, in fact. So you can distinguish the effect of various composition of the universe, and you can determine the composition. But all I want to say is, we now know these compositions, therefore you can get rid of these unwanted oscillations if you're interested in the primordial fluctuations. So this is the power spectrum primordial fluctuations. Indeed, if H function were exactly constant, this is what you will see, the equal amplitude of fluctuations at all angles. But inflation might have done this or might have done that, right? So which one is it? That's the question. So let's parameterize this as a power law. So you have this ns to the -1 power. If ns was 1, we have exactly equal amplitude of waves at all angles. And if ns was less than 1, you will see something like this, the large amplitude of fluctuations on large angular scales and small on small angular scales. This is what we wanted to find for many decades. OK, let's look at WMAP. So WMAP data only, we could find ns was indeed more or less 1 with high precision. But we wanted to go further. We wanted to show that ns is actually less than 1. And for that, we did something like 2.2 sigma hint. Not enough for discovery. But then we can go to ground-based telescopes. So we are limited by angular resolution, right? We could go to 8 of 1,000 And WMAP's dish has the size of 1.5 meter diameter, and it gets you some angular resolution, but not quite too high. So then we go to ground-based telescopes. So you can build 6 meter, 10 meter telescopes on ground. And that will give you much higher angular resolution. Now we can go to L of 2,000 or even more, 3,000, 4,000, no problem. Then with this longer lever arm, we could determine the slope much better. Now we have 3.5 sigma evidence. So we went from hint to evidence. And by adding something like distribution of galaxies, they will also probe the structure somewhat differently. In year 2012, we announced the discovery of NS less than 1 by combining WMAP, these two ground-based telescope, and distribution of galaxies. So that was great. This mission achieved, right? And then, but because it's such an important insight to inflation, namely showing that structures originate from quantum fluctuations, it would be nice to do this from CMB data alone. So a few months after we posted our paper to archive, the Planck team announced the first cosmology result in 2013, and they discovered, got greater than 5 sigma significance, NS less than 1, from the cosmic microwave data alone, combining WMAP and Planck. So that was great. I mean, there's no question that the NS is less than 1, right? So this seemed like a very good proof of inflation, but we might as well be a bit more cautious. How about you seeing epsilon much less than 1? So once again, epsilon is the ratio of the change in h, so h dot over h squared times minus 1. If epsilon was much less than 1, then that's proof that the universe accelerated very, very fast. So this data, the scatter amplitude, is basically proportional to h, as I said, but in detail, it's got little thing here. So it's proportional to 1 over square root of epsilon and something called speed of sound, like Professor Mukhanov showed in 1999. So in principle, you can have a rapidly varying h while rapidly varying epsilon over cs as well. So we want to have something else. I think the evidence is because nobody really thinks that epsilon or cs is really rapidly varying, but just for the sake of completeness. So we want more supporting evidence. I think we have pretty good evidence, but we want more because extraordinary claim requires extraordinary evidence, like Carl Sagan puts it very excellently before. So we want to use gravitational waves. And we'll hear a lot about gravitational waves throughout this conference. That's fantastic. So we're looking at very, very long wavelengths gravitational waves because inflation stretched the wavelengths of the gravitational waves to billions of light years. If you discover gravitational waves of billions of light years, you know that they are not coming from black holes. So the coefficient actually doesn't depend on something that depends on time, as long as they are produced by vacuum fluctuations. I come back to the case where they are not actually vacuum fluctuations, but something else. But this is the basic idea. And then we take the amplitude of the Hij and parameterize that as a parallel. And basically, we wanted to show, first, this thing exists. And if we find it, we want to show that it's more or less scaling invariant, right? So equal amplitude at all wave numbers, primordial ones. But because what we observe is the energy spectrum of gravitational waves today, they are somewhat processed. And here is the x-axis is the frequency of gravitational waves, and y-axis is the energy density in gravitational waves as a function of frequencies. And they have shape, interesting shapes. And with cosmic micro background, we observe gravitational waves of very, very low frequency. But with ground-based laser interferometers such as LIGO, you'll be probing 100 Hertz here. And this thing exists at all frequencies, basically. And you have also pulsar timing array here. And we can map out these gravitational waves at all frequencies. So we are focused on here. But I just want you to know that it's really the tip of iceberg, right? You have the whole experiments from large to small to discover this thing. But since we haven't found it yet, let me talk about something else because it's fun. So basically, the motivation for my research throughout the years is to just keep finding evidence or against inflation. So first test is Gaussianity. So supporting evidence for quantum fluctuations. If there are truly quantum fluctuations in vacuum, the fluctuation should obey Gaussian statistics to high precision. You can test that. So that's the count of number of pixels having certain value of temperature fluctuation as a function of the temperature fluctuation. That's a Gaussian distribution. If you look at the data, that's what I have. So it looks pretty Gaussian, you see. And but you can do better. You can do this. Undergraduate student can do, but you can do better. So you basically say this Gauss distribution is symmetric. This 3-point function, you basically take this histogram, multiply that by temperature value cubed, and integrate, and should be 0 to within the uncertainty of the experiment. Or you can do even better. You look at 3 different locations in space, sky, multiply these 3 temperature values together, and you average over whole sky. Computation intensive, but you can do it. And as a result, we show that with WMAP, possible deviation from the Gaussianity is less than 0.2%. 0.2%, okay? More precisely, we parameterize, this turns out to be a convenient parameterization. So your zeta is a sum of linear part, Gaussian part, and Gaussian part square. So because of this square part, temperature is no longer Gaussian. And you try to constrain this coefficient here. This is the 9-year final result we got. Seems big, but if you realize that zeta here is in fact already 10 to the minus 5, the second term is 10 to the minus 5 times this thing. That's why upper bound is so precise, 0.2%. And Planck didn't find non-Gaussianity either, and improved the upper bound by a factor of 10. So this is a remarkable degree of Gaussianity, and certainly the most Gaussian things I've ever seen in my life. How about vector field? So scalar field, we talked about. Tensor fields, gravitational waves, we talked about. How about vector field? What's wrong with not having it? Well, there's nothing wrong having it, so let's have it. And the vector fields typically, however, just decay, even if they are quantum mechanically produced during inflation. Technical term is they are conformally invariant, so they are not excited. They just see flat inverse from their point of view. But if you couple that vector field explicitly to the scalar field pumps energy into it, and with a bit of heavy lifting, you can make the universe anisotropic. And so now universe expands anisotropically. You see, x direction expands differently from y and z direction. Okay. Now, if this beta were constant, you can absorb this into definition of coordinate. So, but you can't do that if beta is time dependent. So the question is, how large is the beta dot over h to make it dimensionless? Now, if you had only scalar fields, which do not have any preferred directions, then this beta dot just decays by 1 over a cubed. And because a expands exponentially, it's exponentially suppressed. But if you had a vector field, for example, you can keep pumping your energy into creating so-called anisotropic stress in the stress energy tensor that can source. So if you ignore this anisotropic stress here, solution is this. But if you had a source, it makes universe anisotropic. And there's an observational signature of it. Basically, your power spectrum now becomes anisotropic. Usually, when we write down this power spectrum, we say it depends only on the magnitude of k, not the direction. But if the universe expanded anisotropically, during inflation, it's got this term that depends on the preferred direction in space. That's very generic. But if you had a specific model like the one I showed, you can calculate what this is. And basically, you now depend upon the number of V-folds, which is 50 squared here. So it's a big number. And I, that's basically the energy density fraction of vector field. So how much vector field do you have in the early universe? Signature in the CMB. So basically this changes the power of cosmic micro background depending upon the direction. So for example, even if you had perfectly circular hot spot or cold spot in sky, they will be turned elliptical. And they are turned elliptical in some systematic fashion. I'll show you the picture later. So this is a local effect, not the global one. Basically, power spectrum is modified in all directions in sky. Now, there's a beautiful story. In 2007, Ackerman, Carroll, and Wise proposed G-star as a powerful new thing to look at in the data. So we, as data analysts, very excited, right? So once that's claimed, we look for in the data. Then, not us, but these colleagues in Norway discovered it. Surprise, right? Something that was proposed by theorists was confirmed, looked for in the data, and it was found. Beautiful. But then they looked at, so that was a frequency of 94 gigahertz. But oddly, when they looked at 40 gigahertz, the sign was opposite. It's still significant, but the sign was opposite. That was the time when we were like, maybe it's not cosmological. And the preferred direction also happens to be ecliptic pole, if you know what that means, in the sky, and didn't seem cosmological. And in fact, WMAP's beam is elliptical. So even if you see something circular, it will turn elliptical in some systematic fashion. So 90 gigahertz is this, 40 gigahertz is that. So you see that the direction of ellipticity is opposite. And where the WMAP scans the sky in this way or that way. And so it creates a systematic ellipticity in the sky with a preferred direction of ecliptic pole. Well, so if you correct it, then we repeated this exercise on Planck data, found very significant results. But once we removed this beam systematics, so this is the original data, we remove the galaxy because that will create a systematics also. Then using this data, we calculate the likelihood, what the direction where anisotropy is found, that's this, so ecliptic poles. But simulations, without any primordial vector field, but only instrumental effect, we reproduce this exactly. So take the difference, we see no preferred direction anymore. So G star became very significant to non-existent. But then you can learn something from it. So from this limit on G star, we could in fact show that this beta dot by H is less than 10 to the minus 8. So you can have your vector field, but energy density has to be tiny. And the most natural value of this thing is, in fact, either 0.01 or e to the minus 150. So with our upper bound, it looks like we don't really need it. Okay. So recap so far. With WMAP, we found super horizon adiabatic Gaussian primordial fluctuations with NS less than 1. Planck confirmed it and strengthened the limit. We found no evidence for breaking of isotropy. And all the data are wonderfully consistent with the predictions of single field solar inflation model. But we want to find more. Okay? So let's go back to gravitational waves. What we want is to just find it and show that it's nearly scalar invariant. Once found, we do exactly the same thing we did for scalar perturbation, basically to test Gaussianity, to make sure or not it's coming from vacuum fluctuations. Then we construct inflation models, and we celebrate. Okay? So once again, gravitational waves do this. And we hear a lot of talks tomorrow, I think, about how to measure this in practice. So you have two mirrors and laser shot. And then initially, this beam splitter was configured such that when these things come back with the same phase, you flip the phase, and then there's no signal if the distances of these mirrors didn't change. But if gravitational waves passed, it does this or does that, and there's a signal. Okay? That's how you find gravitational waves in practice. And LIGO detected gravitational wave from binary black holes. They announced it with a wavelength of thousands of kilometers, basically the size of the Earth, because that's the maximum you can measure from Earth. But our primordial gravitational waves have billions of light years of wavelength. How do you find it? So we use the universe as a detector. So you have this uniform sea of radiation, cosmic micro background. And when gravitational waves are propagating, it stretches space. If space is stretched, wavelength of the light is also stretched. Therefore, it gets cold when it's stretched, and it gets hot when it's squashed. Yeah? Energy decrease here, increase there. Then you can put electrons there. Imagine that the light was coming from the hot and scattered by electron coming toward you. And what do you see in your radiation? Electromagnetic waves. You see polarization. Okay? Hot thing comes to you with horizontally dominating electromagnetic waves. So this is what you look for. So basically, you need to look for specific pattern of so-called B-mode polarization. Namely, when you have some polarization direction here, you should see 45-degree tilted version from it. And you should see them simultaneously. Okay, not just one, both. We haven't found it. Okay? We haven't found it, and but many ground-based and balloon-borne experiments are taking data now. And it may be tomorrow that we hear the announcement that it's been found. In the meantime, we're developing this satellite with Japanese colleagues. JAXA is the Japanese ESA, Japanese NASA, called Lightbird. And basically, we try to do 100 times better than what Planck satellite, for example, achieved for measuring gravitational waves, with a few thousand superconducting detectors in space. And we have been down-selected by JAXA as one of the 2 competing missions for the launch date in 2025. We are not selected yet, but we hope we will be, and then do this thing. So this tensor to scalar ratio, the amplitude of gravitational waves divided by amplitude of gravitational potential, is what we want to find. And the current upper bound is less than 0.07. With that, you can try to constrain inflation model. So you have this diagram, tensor to scalar ratio in the y-axis, primordial tilt ns, and that was what we had back in 2007. That's the date of the publication. So what we showed, the year we showed this was actually 2006. 3-year, 5-year, 7-year, 9-year. You see how painful this is, okay? And you combine this with ground-based telescopes, you get that. And you combine this with galaxy distribution, you get that. Okay, cool. So now we are there. Okay? Then that red is what we had before Planck results. And this is after Planck. So you see that the upper bound actually didn't change. This model was ruled out many years ago, and it's still ruled out. Yes? But there's an easy fix. In fact, if you had no minimal coupling between scalar field and rich tensor, rich scalar, we showed in 1999 that you can bring this thing down here. And because if you had this no minimal coupling, your potential, steep lambda phi to the 4, gets flattened effectively in Einstein frame, and you can comfortably be consistent with current data. So there are still many models you can have, and many more models are ruled out now that the limit on R has improved so much. So are gravitational waves from vacuum fluctuation in space-time or from sources? So you write down equation motion for gravitational waves, you got a source. Its homogeneous solution is what we typically call vacuum fluctuation. Inhomogeneous solution may exist in this gravitational wave from sources. But if the background spacetime is homogeneous and isotropic, there's a theorem saying that scalar fields, vector fields, can't produce gravitational waves at the linear order. You need to go to second order to produce them. But if you have an SU2 gauge field, SU2 gauge field contains scalar, vector, and tensor in there, in this index. You can have one more index, so you can create tensor out of it. So they can generate gravitational waves at linear order. And if you had this, but again, these massless gauge fields are not excited because they're conformally invariant. You need to break it by coupling it to pseudoscalar axion. Then you pump energy into only right-handed or left-handed gravitational waves. So it's fully chiral. Okay? This is a well-known result, but I want to convey this to gravitational wave community because you can measure, I hope you have a configuration to be able to measure chiralness of gravitational waves, because that contains very rich information But what we discovered very recently, in fact, I hope that the paper will appear in the next couple of weeks, it's non-Gaussian too. And this ratio of the three-point function of gravitational waves, Fourier chiral, divided by its power spectrum is big. This omega A is the energy density fraction of the gauge field, and it can be 10 to the minus 4, 10 to the 4, 10 to the 5, 10 to the 6, millions, right? Whereas vacuum contribution is 1. So imagine that we find, so this is a finishing PhD student in my group. He's a postdoc who recently went back to Japan from Stanford. So thanks to the hard work of these guys, we now have some good, this is the last slide, good program, seems like. First of all, let me emphasize, single field inflation looks very good. We don't have anything that's against it with statistical significance that we take it seriously. Next frontier, we want to use CMB polarization to find gravitational waves from inflation. With Lightbird proposal, we hope to reach R of 0.001. So factor of 100 times better than the current constraint. If we find it, we're not done yet. We have to do our homework. To be able to say we found quantum gravity or quantum fluctuation in space-time, before we say that, we have to make sure that the gravitational waves we found are consistent with Gaussianity. Now, if we weren't, it wouldn't rule out inflation. In fact, this thing was produced by inflation, gauge field during inflation, but that actually tells us potentially even more exciting thing, right? So gauge field existed during inflation, and that's an open the window to new physics. And I stop here. Thank you very much.
So we have some time for questions.
One of your early slides, you put a plot of the current day energy density as a function of frequency from cosmological to high frequency, with showing before and after parts that entered the horizon before and after matter. There, what are the wiggles there around 10 to the minus 10, 10 to the minus 6 hertz?
Yes, thank you for asking. That's the point of this paper here. So radiation-dominated era. And it will be completely flat like this if the radiation energy goes down like 1 over 8 to the 4. But radiation contents change. Electron and positron annihilate. QCD phase transition, maybe SUSY. They change suddenly the energy density in radiation. So you can have electron-positron annihilation here, and it creates some weird feature here. QCD phase transition here. So this is like a time machine. You map. It's often said that we don't know anything about expansion history of the universe between, let's say, inflation and matter radiation equality. With this, in principle, you can map out the whole expansion history, whole evolution of radiation contents in the universe.
This might be a naive question, but I was wondering, so we talked about scalar fields and scalar fields coupled with vector fields which can drive inflation. I'm just wondering if there is let's say a 4 Fermi kind of theory which can drive inflation, and then it leads to condensation at some critical temperature leading to a scalar field-like theory. What would that mean for the isotropicity or the Gaussianity of the background?
Right, it's not a naive question at all. I don't have any idea. But yeah, I mean, so people, but all I can say is I think that's the kind of question we should ask, right? So we'll be often told that the inflation homogenizes everything, isotropize everything, no signature of isotropy in there. That's not necessarily true. And if you had a model or theory, 4 forms or anything, that can possibly generate or produce some preferred direction in space, or produce gravitational waves in a different way, that's worth investigating. And they tell us what we should look for, because we're kind of getting bored of measuring the same things over and over again. But very, very excited to be told to look for, hey, preferred direction. You learned from textbook that there's no preferred direction in the sky, right? But did you look? And we learned something new there. So
perhaps one last question over there for the microphone.
So, Eiichiro, with the measuring the polarization in the CMB down to this 10 to the minus 3 level,
yes.
So to begin with, I think it's challenging. You've got your dust foreground, you've got your gravitational lensing, and all of that to try and dig through.
Yes.
After doing all of that,
yes.
I'm assuming that the possibility of having various non-Gaussian signatures from the removal of the foregrounds.
Yes, yes.
This can be quite challenging. I mean, what do you think the prospects really are to be able to make that kind of separation?
Yeah, thank you for the question. So if we wanted to do generic non-Gaussian studies, there's no hope because of the foreground. But we have a model that gives us a specific prediction for the shape. So this is just an amplitude, but this bispectrum has dependence on K1, K2, K3. You have a specific template to look for, which wouldn't be the same as foreground. In fact, the same story was true for scalar modes. And there was serious doubt whether we ever get to noise-limited measurement of the non-Gaussianity. We've done it. And this will be, no doubt, it will be more challenging. But I hope that we'll do it.